What is the meaning of dispersion diagram? A dispersion diagram is a graph that shows how the frequency of a wave varies with its wave vector or propagation constant in a given medium or a structure. That it shows a relation between frequency and propagation constant. So what kind of information we will get from the dispersion diagram? It tells that how electromagnetic wave travel inside a structure, which frequencies are allowed or not allowed. It shows the electromagnetic band gap, that which frequency component or which band will be allowed for the propagation and which frequency band is not allowed for the propagation from the structure, and how fast energy moves, that is group velocity. So all these kind of information we will get from the dispersion diagram. So it is mostly applicable for the metamaterial, and metamaterials are there are several kind of metamaterials. So in this discussion we will consider the mushroom like metamaterial structure, and we will create the dispersion diagram for that kind of structure. This arrangement, which is taken from the EM Talk website, shows the periodic structure. In this periodic structure, we have 4 unit cells, and each unit cell is a mushroom-like structure. So here we can see that there is a patch, which is a conducting material, and there is a via. It is again also a thin wire conductor, and there is a conducting ground plane. So here we can see that they are there are 2 conductors and sorting via via. If you plot the equivalent circuit diagram of this structure, then what you will find that there is a conducting surface. Which there is a conducting surface. It will represent an inductor, and this gap will represent the capacitance part. And again, the next conducting structure will represent the inductive part. And these both of inductors are short or in series. So the equivalent diagram will be there is an inductor and then capacitor and inductor. So capacitor will sandwich in between 2 inductors, and there is a ground plane. So this structure is a high impedance surface, and it is act like a artificial magnetic conductor, AMC. It's a type of metamaterial or left hand metamaterial. Left hand metamaterial means it consists negative refractive index. So the value of theta is less than 1, and it will propagate the backward transverse electromagnetic wave or QC transverse electromagnetic wave, because uh, patch antenna always supports the QC transverse electromagnetic waves. The waves will be propagated in the backward direction. So in HFSS, we will develop the single unit cell of this mushroom-like structure, and then we will plot the dispersion diagram and see that which kind of band it is passing. Now we will see that how to plot the dispersion diagram for a unit cell. So we are using the Ansys Electromagnetic Desktop 2021 R1 software. In this, first we go on the HFSS, then solution type, and switch on the Eigenmode. What is the meaning of Eigenmode? Eigenmode is a natural electromagnetic field pattern of a structure without applying the external excitation. So for any metamaterial unit cell, we will not apply any kind of excitation, and then see that the behavior of electromagnetic waves, and this is called the Eigenmode. So when we obtain, it is obtained by solving the Maxwell equations with boundary conditions. So what we will do, we will apply the boundary conditions to our structure and apply the periodicity, that is Bloch-Floquet condition, to our structure, but we will not apply the any kind of excitation, then we will get the eigenmode solution of our structure. So when we will plot the dispersion diagram, we will solve these kind of wave equations. These are Maxwell's equation. So in this equation, this omega represent the eigenvalues, and the pattern of E and H field is represent the eigenvector. And each curve is the dispersion curve of for a single mode. If you select more than one mode, that becomes the higher mode. So fundamental mode is the eigenmode 1, and rest of the modes are the higher order modes. Now first we will create the ground. So we select the plane. Now we will provide the dimension. Dimension of our ground plane is 5 by 5, and it will be half of 5, so it is minus 2.5. It is also minus 2.50. Then apply. Okay. We will name this is ground. Provide some color. Provide some transparency. In the second step, we will select this box to make the substrate. The length and width of the substrate will remain same, but the height of the substrate, it will be 1.27 mm, and starting points are, it will remain same. Now we will provide the name substrate. We will provide the material is RT duroid. So there are several kind of RT duroids are here. We will select 6010 LM trademark. Now we will create the page over it. Again, we select the sheet. Its dimension is 4.8 by 4.8. So it will be minus 2.4. This will also minus 2.4, and we will insert the page at the height of 1.27 mm. We will provide the name page. We use some different color and transparency. So now we create the page. In the next step, we will insert the via. So for inserting via, we have to create a hole in the substrate, and then we will insert the via. Via means it's a conducting thin wire. So what we will do, we will create a cylinder. So for creating the cylinder, we choose the center point. Now the center position of the cylinder is 0, 0, 0. Its radius is 0.12 mm. Its height will remain same as the height of the substrate. This is 1.27 mm. Now what we will do, we will create, we will copy and paste the same cylinder, and we will subtract the cylinder 1 from the substrate. So it will make the hole, and cylinder 2 will remain insert in it. By selecting these two, we will use subtract. So here we subtracted the cylinder 1. Now cylinder 2 remains same in it. We will provide some color, some transparency, and rename it by via and provide the material copper. So we have completed these steps. Now we will create the airbox to apply the boundary condition for this unit cell. So here we can see it's a mushroom-like structure. There is a kind of a page and there is a via at the center of the page. So, and there is a ground plane. So we have three contacting portion: page, via, and the ground. So here we can check one more time. We have not assigned any boundary for ground and page. So we apply boundary perfectly, and we will also apply boundary perfectly for both. So now it is okay. Ground and page perfectly, roser, substrate, and copper here. Now we will create the box. So what should be the dimension of the box? Actually, there is a thumb rule that it should be the sixth time of the height of the substrate. So we will these are the same. These are the starting points. This is the size of length and width, and height should be 10 mm. Now this is our air box. So rename it by air box. You can provide air to it, or you can make it leave as it is, like vacuum. Now we will press the F key on the keyboard. So it will select a face of the structure. First we will select the top face of this airbox and then apply the boundary, and in this boundary we will apply the PML. So this is the PML wizard. It will automatically give you the dimension. So just you have to click on next. The minimum frequency, we are supposed that our minimum frequency is 1 gigahertz. So it is okay. It is all okay. You can see that a perfect PML, perfect magnetic layer is insert over it. Right. So here in boundaries you can see that this is perfect E1, perfect E2, and this is PML group you can see here. So we have completed here the designing of the structure. Now we will provide the boundary condition and periodicity to our structure. To provide the boundary conditions, first we will select this surface. You can see here this is the x-axis. Okay. So first you select the surface which is parallel to x-axis and perpendicular to the y-axis. So for the first, you will select the surface, right click it, and then apply boundary condition, then go in the coupled, then primary, where you will select the primary one. You have to define new vector u. This vector always will define from negative to positive direction. And when you will define the u vector, it will automatically take the v vector perpendicular to the u. So we have to make, okay, this is our primary or master boundary. And similarly, apply boundary coupled. Now we have to create the secondary boundary for primary boundary 1. So this is secondary one. Primary boundary, we have primary 1. Again, new vector, and it is again from positive x direction. So all this is okay. Now for phase, this is px. You have to write perpendicular phase here. So you will write py, and the initial value of py is 0 degree. Okay. Now we will do the same exercise for another two surfaces. We will select this, assign boundary, coupled, primary to new vector. We will define it in positive y direction, so from this point to this point. Okay. And it is a secondary for primary to assign boundary, coupled, secondary for primary to define new vector in positive y direction. Next, here we will provide the phase delay. We will make it variable. So it will be px because it is perpendicular to the x component. So it is px, and we will put the value of px is 180 degrees. So here we can check one more, primary 1, and this is the corresponding secondary 1, and this is primary 2, and this is the corresponding secondary 2. So we provided the boundary condition, and these boundary conditions, that is master and slave boundaries, are applied for the periodic structure, right? So this our this unit cell shows the periodicity, and the value of px py, it shows the value of px, and py is the phase value of this for this boundary condition. Now we will apply the analysis setup. So we'll do add the solution setup. In this, we take minimum frequency as 1 gigahertz, and we are not only to see the fundamental mode, we are also interested in higher modes. So here we can put value 3, so it will provide the 3, not only fundamental mode but also 2 other modes. Number of passes, we can make it 20. then OK. So first check the validation, all good. Now, what is the Bloch theory? In a periodic structure, this is the Bloch diagram. So here, what happened? The wave repeats after unit cell. Means wave will pass from one unit cell and enter into the another unit cell. So when it will another into the second unit cell, it should be periodic in nature. Okay. So the nature of the wave should be repeated. So according to Bloch theorem, we have a value gamma where kx and ky is the wave number. So initial point, we are taking it as 0. So from this 0 point for initial stage, the wave will propagate in this direction. The component of the wave will propagate in this direction. Okay. So here x is increasing, and at this point the phase value should be 180 degree. So this point is the x point, and x equal to, for the second point, 180 degree, and there is no variation in the y component, so it will remain 0. Okay. So first we will move from gamma to x, then in the second stage x to m point. So in here this point is constant and the variation in the y direction. So again the phase change from for the y component from 0 to 180 degree. So here you can see that both of the points are at m point, both of the values will be 180 degree, right? And then you will move again at the center point. So from m to gamma you will again move from this path, and this value will again 0 0. Okay. So according to the Bloch theorem, 0 degree gamma, 180 degree x, 360 degree m, and 540 degree gamma. So there are differences of 180, 180, 180. So total 540 degree. Same concept we will provide here. So in optimetric, add parametric, and in parametric we will add now. First we will select px. It will start from 0. It will end at 180 degree. Steps, you can say this is our resolution. We are taking 15 degree as a step. These are the linear steps, so we select this linear step here. Okay, so we add this, and for this condition the py will remain same at 0 value in the entire propagation. So this is our first optimetric. We will select it. Okay. Similarly, we will add the next parametric value. So here the py will change from 0 to 180 degree in the steps of 15, and the px will remain same, that is 180 degree. So single value, we will add this. Okay. Okay. So here the value of Px is 180 degree and Py is varying from 0 to 180 degree. Similarly, we will add parametric 3. Here we will Px is 0 to 180 degree in the steps of 15, and similarly Py will also 0 to 180 degree in the steps of 15. We will add both values, and there is a point that first you will select both of the values and you will do the sync. So actually, what is the meaning of sync? Over here you can see the table that it is coming like 0, 0, 15, 0, 30, 0, 45. Okay. So what happened when we will apply the sync option? Then here you can see 0, 0, 15, 15, 30, 30, 45, 45, same values are here. Okay. That is the meaning of syncing. Now we have create all three optometrics. We have already added analysis setup. Now we will just go on analyze all. So after completing the execution process, now we will see the result. Go in the HFSS, in the result portion, create Eigenmode parameter report, rectangular plot. Then we will see the result for all three modes. These values will take the real values only. Okay. Then new report. So here we can see that this kind of graph we are getting, but we are not able to make any kind of conclusion about our structure, how it disperses with respect to frequency. So what we will do, first we will export the result on desktop. We are taking this three. Now this is our result. So again here you can see that the results are not in the exact manner what we have to require. What we will do, first we will arrange them as per the this Bloch theorem or Bloch diagram. This is Bloch-Benjamin curve. So first we have varying x and we keep the y constant. So we will select all that values where x is varying. So where x is varying and y is constant. So it is 0, 0, 15, 0, 0, 0, 15, 0, 30, 0, 45, 0, 60, 0, 75, 0, 90, 0, 105, 0, 120, 0, 135, 150, 165, 180. This is our complete cycle for x. Just copy and paste them here. Now fixed value of x 180 and y will varying from 0 to 180, right? So 180 and 0 is the first combination and rest of the combinations are here. Here we can see that the value of x is 0 and y is varying from 15 to 0 to 180 degree. So just copy and paste. Now we have to require those values for which all the values is same and they will move from 180 point to 0 point. So we will move in the backward direction. So we have 180, then 165, then 150, then 135, 135, 120, 120, 105, 105, 90, 90, 75, 75, 60, 60, 45, 45, 30, 30, 15, 15, and finally we have to take the value 0, 0, right? This is our mode 1, then mode 2, then mode 3. Now we have not required phi 1 and phi 2 values here. We maybe delete. Angle is required and it is shifting by every 15 steps. So from 0 to 540 degree, we have all these angles. Now we will plot the curve. So this is our graph, and here we can see that these are the band gap between different frequencies. So here you can see that where is the steep slope. So at these points we have steep slopes. So if we plot a line here, okay, or you can say like this. So these steep line, it represents the change in energy. So here on the reference of this line, the energy is changing rapidly. And similarly, the starting point and the end point of the curve must be same. If this is same, that validates our periodic structure. Otherwise, the structure is not periodic. And and you can see here that there is a negative slope line. So the negative, what is the meaning of negative slope line? So the meaning of negative slope line is that this is the group velocity, that is dw upon dk, change in frequency with respect to wave number. If it is less than 0, it shows the backward waves. Okay. The entire portion where the slope line is negative, it shows the backward wave, or the nature of the material is double negative, or it become a metamaterial. So here energy and phase moves in the opposite direction. So if the group velocity, the slope shows the group velocity of the curve, flat region shows the slow waves, and steep region shows the fast wave. So here in our result, this is mode 1, and this is our fundamental mode. And here you can see that maximum portion of this is the flat, and it means it represents the slow wave structure. So this is a fundamental theory of the dispersion diagram. Thank you. Now we